So at this point, it's probably worth emphasizing that if you show that a series converges absolutely, that will mean that the original series converges. That's a theorem. However, if you show that a series diverges absolutely, that does not mean that your original series diverges or converges. You just don't know. You have to go back and test the original series using other methods. All right, so our point here is, as we've shown, you cannot generally deduce convergence or divergence of a series from knowing that the series diverges absolutely. Now, having said that, along comes a new upgraded version of the ratio test that in some cases allows us to deduce divergence from absolute divergence. So this is the ratio test that we studied previously, which has been upgraded a little bit to account for series with terms of any type, as long as we have non-zero terms. So this is a series of positive or alternating or terms that have no pattern in their signs, any series at all. All right? This is a very powerful theorem and one that you will use a lot in determining absolute convergence compared with the other tests. And so what does it say? It says if you take the positive ratio of the k plus first term over the kth term and get a ratio less than 1, then your series converges absolutely, which means that the original series converges. If the ratio is greater than 1 or infinity, then your original series diverges. This is the part that's more powerful than what we're able to do with other tests. We can actually deduce, if we know this, that our original series diverges. And if the ratio is 1, then there's no conclusion we can make about the original series. Now you might wonder, well, if this test is so great and powerful, why didn't I use it on the 2 examples in my last video? The problem is this test wouldn't have worked in my first 2 examples. In the second example, had I used the ratio test to test the original series for convergence or divergence, I would have had a ratio of 1 and it would have been inconclusive, and I would have had to have gone to another test anyway. But here's an example where the ratio test for absolute convergence works very nicely. So with the ratio test for absolute convergence, I want to compare the k plus first term to the kth term of positive terms. So I don't need to take the negative 1 to the k, since that's the sign part of the sign change. So I'm going to do the limit k plus first term divided by the kth term. And simplifying, I can factor k factorial numerator and denominator, which leaves me with k up here, and subtract the exponents, which leaves me with 2 down there. Take the limit, and that goes to infinity. And since my limit of ratios goes to infinity, I therefore know that my original series diverges. So since the limit as k goes to infinity of the absolute value of the k plus first term over the kth term equals infinity, this part here being a sub k, therefore by the ratio test for absolute convergence, the original series diverges.